really interesting application of light are the behavior of mirrors and lenses. Of course, we all look in the mirror probably every morning trying to get dressed for the day. Many of us wear glasses. Some of you use microscopes in your lab classes. You look through telescopes to go see the stars. So many different applications. So I like this first image right here because just looking at a spoon, when you look at one side of a spoon and look at yourself on the other side of the spoon, you get different images. So I do recommend grab if you have a metal spoon, see what it looks like, move your spoon towards and away, flip it around, look at the convex, concave side. Convex is the side when you're looking with your eye that it sticks out. Concave would be the opposite. It caves in when you look at it with your eye. And see what the difference is between the behavior of the mirror. So this one over here, this is going to be your concave mirror, and you're going to have your convex mirror over here on this side. And so we can see that the images change and vary. There's some weird stretching going on this one. Okay, you can see like the head shape is very, very different. And you can see there's differences in the size, like this head, this face over here is much bigger on that side than it is over here on that side. And this one's obviously upside down, which is kind of weird. So what produces these different images? Now, this is one of my favorite things about physics. I love learning how to figure out what these images are going to look at. It's going to be a lot of diagram drawing. There are some calculations that go along with it, but for me, it's really just kind of seeing how we can make predictions about the images that are formed. And then you're going to play around with lab simulation to be able to see if your predictions are actually what happens. So in reality, every object is emanating light because light is bouncing off and reflecting. So, but if we picture a point source of light, that our light was actually being generated by a single point, those light rays actually travel out 360 degrees in all directions. Now, we assume that they move with straight lines until they hit off of a reflective surface, and then they are going to bounce. We saw reflection earlier. So reflection, they are going to bounce off at the same angle that they came in at. And what ends up happening is those light rays get scattered, and some of those rays will intersect your eye. Now, what we actually see when we look into a mirror is going to be the image. And what's really weird is because in many cases, when we look at a mirror, in these cases, this is called a plane mirror because it's flat. It's a plane in space. Is what we're actually seeing of the image is not coming directly into our eyes. What ends up happening is if you trace back all of the rays that are bouncing off in all these different directions, and you trace them kind of backwards into the back side of the mirror, and we use these little hashes here to show the back side of the mirror, and then this is the front. So this is the shiny reflective side over here. And then what ends up happening is if you trace these light rays back to the back side of the mirror, what we're actually seeing in the image is behind the mirror. So when you look at a mirror, it looks like what you're seeing is behind the mirror. So we use kind of different symbols for this. So what the image that we see, we use this little prime, the little apostrophe up top to represent the image. So the properties of the image are always going to be represented with the prime. A is our actual object. So the image is what our eyes will see. Now, the outgoing rays don't actually intersect. What we see is this image formed back here. Now, because the image, the convergence of the rays, where the rays converge, is actually behind the mirror, we call this a virtual image because it's not the actual rays that are converging. It's these backward rays that we're tracing back. They're virtual. So we're not actually seeing the object. We're seeing a virtual image of the object, a projection, if you want to think of it like that. Now, most of our objects are not points in space emanating light. They're made of a whole bunch of basically reflections of light. So if we've got this little green rectangle here with this red triangle in there, every point on this object acts as a light source because light is bouncing off of this object. So every point of this object is making its own image in the mirror. And when you look at all of those images that are creating by every single point on the object, that is the overall image that we're seeing. So you take this little point right here, that little point right there is having a ray that is going to bounce off. Once again, it's going to bounce off at the same angle that it leaves, that it arrived with. And that point is creating an image. So that point is creating an image back here. Once again, you trace the ray backwards for these plane mirrors. If you take a different point, this point right here on the image is going to have the same properties. So that light ray is going to get reflected and it's going to be at a different location. And if you were to trace these rays for every single point on the object, you would end up getting an image and getting a creation of that image. Now, because those rays are coming off in all different directions, each point is creating rays in all directions. So to know where a point is going to be, if you were to do multiple rays and trace multiple rays, so the red and the blue rays for this point, then what ends up happening is I've got a confirmation that because two sets of rays intersect in the same location, that has to be where that point of that object is going to be. And you could trace all of those back. Now, if we want to quantitative, so with numbers, describe our image, we use Y for the height of the image, or height of the object. So this is the object side. And this is the image side. So Y is the original height of the object, so Y prime is the height of the image. So that's our height for the image. We use S for distance. So that's the distance from the mirror to the object. And then S prime would be the distance for our image. Now, depending on the textbook that you're using, depending on the website, they may use H's instead of Y's. They may use D's instead of distance. Sometimes I see like HO for the height of the object, HI for the height of the image, DO for the distance of the object, DI for the distance of the image. I was always taught Y and S, Y prime and S prime, so that's the way that I do my formulas. So I think that's the way that they're shown on the formula sheet. But no matter how you write the formulas, they're the same. So one thing that is true for a plane mirror, and this is for plane mirrors, we're going to look at the curved mirrors in a bit, but the object distance and the image distance are the same. But we use this negative to imply that we are behind the mirror. So the negative sign implies that we are behind the mirror. We'll talk about sign conventions kind of as we go. But in this case, negative means behind the mirror for a plane mirror. The relationship between Y and Y prime for a plane mirror is that they're the same. So they're always going to be the same. Magnification is always calculated as the ratio of Y prime to Y. And for a plane mirror, it's always 1. So when you have a flat plane mirror, the distance is always equal to the distance from the mirror, but on the opposite side. And you could test this. Go look at the mirror in your house and see if this is true. And then our value, though, we call S prime negative because it's located behind the mirror. Our objects are the same height. Therefore, the magnification is 1. And they don't, there's no, and the images are upright. So the image doesn't flip upside down. Okay, they're specifically for a plane mirror. So all plane mirrors produce images that are upright, virtual because they're behind. Okay, our negative implies that it's virtual because it's behind the mirror. And the same size. They're also reversed front to back, so that means your left and your right switch. I think you can recognize that when you look at a mirror. So here's a cool little question. How tall must a full-length mirror be? If you're 6 foot tall, do you need a 6 foot tall mirror in order to see yourself? Well, let's picture that your eyes are actually at the exact top of your head. Let's pretend, because it's a little bit easier. If we pick a light ray from the top of your head, we pick that light ray going straight across. And so it's going to bounce right back. And we trace that back, it's going to hit the top of your head. Now, yeah, top of your head is making a bunch of different light rays. So what about another light ray? Okay, so what about from your foot? What about where does your foot have to hit? So our foot is going to come up here. So we picture one going up here to reach your eyes. In order for it to reach your eye, which we're assuming, once again, it's at the exact top of your head, in order for your incoming and your outgoing rays to be identical at that angle, that just has to hit at the midpoint. So really, our mirror, in order to see everything, only has to be half the height of your body. And it would have to be at the top half. So you might notice that if you have one of those like freestanding mirrors, that if you put it on the ground, you're not probably going to see yourself very well. But if you put it up higher, you can actually see yourself in a full standing mirror that is only half your height. Kind of cool little fact. Now, most of what we're going to spend our time on is spherical mirrors. So if you picture that you have a polished surface. So for example, most mirrors have like some sort of like, old mirrors were like silver, but now you can use like aluminum foil, has like a background and then there's glass on top of it. So as long as you've got that polished surface, picture that you've made that surface that is cut from a perfect circle. So our mirror is only going to be a portion of that, a part of the arc of that sphere. So we define C, capital C, to be the center of the original sphere. We call it the center of curvature. So you can see C is going to be at the center. Now we wouldn't be able to see the whole sphere, but that would be a value. We call the vertex is the center of the mirror segment. So it's the part that sticks out the furthest. Okay, that's the vertex. And then our radius of curvature R is the radius of the sphere. So basically the distance between the vertex V and the center of curvature C. And then if you were to create an axis, we call the principal axis the axis that goes through C and V. Sometimes it's called the optical axis. So we use that as kind of the midpoint, and we'll use that in our diagrams. So what we're going to do is we're going to create ray diagrams. So these are called paraxial rays. They are parallel to the principal axis. They get reflected through a common point, which is the focal point. So when you have rays that are parallel coming in, they will always pass through the focal point. We also call the focal point the focus. We use a capital F for that. I've seen it as a lowercase f as well. So here's an example of paraxial ray. Each one of those, if you were to take these parallel light rays, they would all pass through the focus F. So for example, pick a laser pointer. Laser pointers are really nice because they create that, that single ray of line. And if you were to move that laser pointer, keeping it parallel to our central axis, they would all meet at point F. So that's a way you could experimentally determine the focal point, is where those different laser lights would meet. Now, the focal length, lowercase f, is that distance. Okay, so capital F is your focal point. Lowercase f is this distance right here. Okay, so that would be our lowercase f. It is always going to be half the radius of curvature, so r. Oop, there it goes. Sorry, it was already drawn. Just didn't hit the next arrow. So there are two types of mirrors. We've got our concave and our convex. So once again, if you're looking at the shiny side is on this side. So this is the not shiny side. Sometimes we see them written like that. Okay, the not shiny side gets the little lines. If it caves in, that's concave. If it comes out towards you, that's convex. So when the curved shiny part points out towards you, convex. If it bends away from you, that is concave. Okay, so the behavior of these mirrors are different. Sometimes we call concave mirrors converging. They're often called converging mirrors because you can see that the tendency of the light rays is to converge, although it's not 100%. And then convex are often called diverging mirrors because you can see the light rays tend to bounce away from each other. So when we draw diagrams, we're going to trace the rays, the light rays that come through. These are called principal rays. There are different rays that you can draw. At a minimum, you have to have two rays that intersect, and then you can draw an image. So these are ray diagrams. I love drawing these. You'll get practice doing these in the lab. Your lab's a little bit longer, but that's because you have a lot of different options that you need to explore. Instead of me doing them all up here for video, you're going to get to see and practice doing these in the lab. So we usually represent our object as an arrow. We use an arrow because that way it has a direction so we can see if it gets flipped upside down or not. So that's what our object is going to tend to be. If you were doing this lab in person, different ways we can do that. Sometimes you use a candle and then you can actually see the flame upside down, or there's actual like light boxes that you use like a light source and you put like a little filter in front of it that actually has like an arrow on it so you can see the light ray. Everything blocks but the arrow. So the arrow is commonly used, or a candle. So I think I learned it in high school. We would just draw the candle. Ooh, got your candle flame. And then you'd be able to see if the candle got flipped upside down or not. So the first possible ray that you can draw, and I usually draw this one because this is really easy to draw, you go parallel to the axis. So you go from the top. We always go from the top of the object. We don't have to do any of the other rays except for the ones that start at the top of the object. We go directly parallel and then it passes through the focal point. So that's the first possible ray. I draw that one every time. It's a really easy one to draw. The second ray is the other one that I prefer to draw. Goes from the top, you pass through the focal point, and then you come parallel. Okay, so that one leaves parallel, this one enters parallel. And you can see that those two rays intersect right here. So if I wanted to, with just those two rays, that's where my image should form. So I can come here and I would draw my image. It would be upside down. And I could see that that is shorter, it's upside down, and it's moved closer to the mirror than it was originally. But there are other rays that you can draw, and sometimes people like to draw 3 rays to make sure that all 3 rays will connect at the same location. So the third ray passes through the center of curvature. Because you're passing through the center of curvature, it's going to reflect back in on itself. So that one you could also draw, and we can see that all of those rays are going to intersect in the same location. The fourth ray, I don't ever do this one because it's really too complicated. You'd have to get a protractor out, but it's the one that goes through the vertex, and the one of the vertex is going to have the angles that are perfectly mirrored on either side. You can see that ray passes through. That one I find is just too hard for me to draw without getting out a protractor. So you only need 2 rays to be able to predict the image, but if you're not sure, it's good to draw 3, because for example, I've got some rays that are intersecting here at other locations. So if you wanted to double check, 3 rays are better than 2, because then you know at least there's where the image really should be with 3 rays. All right, so when we draw ray diagrams for concave mirrors, we are going to follow the same procedure we just talked about. But what's complicated about concave mirrors is that the results are going to vary depending on where the object is located. And you don't have to memorize this because you can actually draw the ray diagrams and make the predictions yourself, as long as you're approximate. Okay, so you do want to kind of be careful about it, like if you're working on scratch paper, to try and keep everything as proportional as possible. But if you have your object outside the center, so if you're bigger than the center, like which this is actually shown, what happens is the image is going to be real. It's real because it forms on the same side as the object. Okay, that's what real is. Real is it's forming on the same side. Now, inverted means upside down. And of course, it's going to be smaller or reduced. Now, here's the trick. If you were to put your eye right here, you would not be able to see anything because our eyes see virtual images. So if we were doing this lab, if you were to put your eye at that location, you would not be able to see it, even if you got the location perfect. What would happen though is if you put a screen, so we usually use like a note card, if you were to put like a white note card at that location, that image would actually be projected onto that note card. So if you were to look at the back side of the mirror side of the note card, you would be able to see an image there, but our eyes are going to see virtual images. So we would not be able to see that image. We don't see the real images, but it would be projected onto that screen. This is essentially what a telescope does. If we have an object that instead is closer and inside, so between F and 2F, so if I was to start my image here, we would see something different. And you would trace your rays. So this first red-orange ray would actually be the same. So this one here would be the same. It would come across, it'd go through the focal point. Now, what would end up happening is if we did the second ray, the blue ray, that would actually have to come down, straight down here through the focal point, and it would come across over here. And if we look, where would those rays actually meet? Those rays would meet over here. And my image would be formed outside my center of curvature. It would be upside down, so it would be inverted. It's still real because it's on the object side of the mirror, and now it's larger. That's kind of what a microscope does. It makes our images larger. Now, our telescopes and microscopes, telescopes are sometimes a combination of mirrors and lenses. Microscopes are based on lenses, but that's the idea, okay? Microscopes make things bigger. Telescopes tend to make things a little bit smaller. Now, if you were to put the object actually at the focal point, weird things are going to happen. Because what ends up happening is our object is already at the focal point. So it's actually not going to, you can't really draw ray 2. Ray 2 would never hit the mirror. And if you were going to try and do 3, well, what ends up happening is if you go through the center of curvature, it goes that way. Well, it's never going to reflect back on itself. And you can see that these rays are parallel. And so if you put an object at the focal point, you actually won't be able to see it. No image is going to be formed when you are at the focal point. You'll be able to see that in your lab. And then if we were to actually move it closer and move it inside the focal point, so once again, that red ray is going to be the same. Okay, so it's going to come across, come back through the focal point. If we were to do the blue ray, the problem with the blue ray is that it's not going to actually hit the mirror if it comes directly through like this. But we can actually project what it would do if it was coming through. and you actually make the rays that kind of go back behind, so when it's inside. And so what ends up happening is you will start to see where do the rays intersect on the backside, and we're actually going to get virtual images when you go inside that focal point. Like I said, you get to play around with that in your lab. And here is that example, okay, because it's a different process. So this is like a shaving mirror, because we need it in order to be able to actually see the image. So makeup mirror, shaving mirror, either way. If we go through and do our rays, ray 1 goes through the focal point. So we're going to have to trace the rays backward, and it's the reflected rays that you trace backwards. Ray 2 goes up and is going to reflect, okay, so it's going to come back through, and we're going to go backwards. And we can already see where that image is going to start to form. Ray 3 is going to reflect back through, and you can see that that's going to continue straight through the mirror. Oh, and they didn't do ray 4 for us, but that's okay. So we would actually be able to see this with our eyes. Okay, if you were to put your eye out here, of course, on the side of the mirror, we would see, which is over here. If you were to put your eye over here, you would be able to see that image. The real images we can't see. So this is a virtual image. It's upright and it is larger, and that's going to be true anywhere in this range. And you're just going to see that as you move the object, and you can do that like in the simulations, that it's going to change the size and how much bigger it is, that magnification factor. So the mirror equation that we have here is 1 over s plus 1 over s prime is equal to 1 over f. And f is equal to r over 2. And so you could plug in r if you know it, because r is that center of curvature. So sometimes they give you r, sometimes they give you f, but they're related. And then if you use a plane mirror, the focal point of a plane mirror is infinity. And if you were to plug 1 over infinity, you get 0. And so you would get 0 over here. And that just gives you that 1 over s is equal to negative 1 over s prime. And then if you invert, you get s is equal to negative s prime, which is what we said was true for a plane mirror. So this equation works for all mirrors. And so what will end up happening is you're going to get different values. So s prime is the distance for the image. Y prime is the height of the image. So from the magnification, you get your y prime over y. And that's also equal to negative s prime over s. So you can use either the distance or the height to make those calculations. You just have to be really careful, because if you are using s instead of y, you need that negative right there. And so that negative is also going to help us with real versus virtual. And so that's going to relate to our sign conventions. So these are true all the time. So we have to come up with our rules for how we're going to know what's positive and what's negative. So our object distance s is positive if the object is on the side of incoming light. And that's what we assume is true. Okay. So our incoming light. So our light would be coming in from this direction, right? Towards the mirror. S prime is positive if the image is on the side of outgoing light. So because this is a mirror, our mirrors are going to reflect light backwards. So S prime is on the side of outgoing light. When it's on this side, then it's positive. If we have that virtual image and our S prime was on the back side, there's actually no light over here, okay, because we're behind that mirror. That mirror is a solid surface, right? No light is actually passing through the mirror. It just appears to. And so that would be a negative value for S prime. And so that's going to be the big thing that you kind of have to memorize for the equations. And then the focal length F and R are positive if on the side of outgoing light. So here, our center of curvature and therefore our focal point are on the side of the outgoing light, the side that the light leaves the mirror. So we start thinking of reflection, okay, where the light rays go when they're reflected is the outgoing side. This will be a little different when we do lenses, because lenses, the light passes through the lens and it's a little different. And then your image height y prime is always positive if the image is upright and negative if the image is inverted. So this would be a negative value for y prime in this case. So we can see when you look at that magnification that in this case our magnification would be a negative value for y prime and a positive value for y. So that's going to give us a magnification that is negative. And when our magnification is negative, our image is going to be inverted. So we can see that from our magnification equation, that anytime your m calculates as negative, it's inverted. When m is greater than 1, then that means your image has gotten larger. When m is less than 1, that means our image is smaller than the original object. And when our m is negative, that is inverted. Okay, so we can see that from our formulas, and if you start looking and comparing at different things. We can also see that here we've got S prime and S would actually in this case both be positive. So in order to get that negative magnification, I would have to add the negative when using S prime and S. Whereas when you do Y prime and Y, because your Y prime comes out negative because it's inverted upside down, you don't need that extra negative there. And these equations, and therefore the sign conventions, are valid for all mirrors and lenses. So these are the rules for the sign conventions. It's just gonna be applied a little bit differently with the lens, because your light doesn't get reflected; it gets refracted passing through. So some applications of concave mirrors. Lots of different things here. So satellite dishes are concave. They don't reflect visible light. We tend to use them for different waves. So with our like flashlights, headlamps, stove reflectors, so anything that is designed to kind of make our light brighter, anything that we have like these different types of mirrors to make things bigger when you get inside that focal point and so forth. So convex mirrors are a little bit different. So because these are diverging, the light rays are always going to go into the virtual range. So in this case, our reflective surface is over on the left. Okay, so remember, no light actually passes through the mirror. So the center of curvature is now on the opposite side as the incoming light. Our focal point is on the opposite side of the incoming light. If we draw our rays, then our first one is going to get reflected. Now, how do we know what angle to go out? Well, what you do is you go from this point of intersection right here where it goes parallel, and then you trace it backward to the focal point, and then you trace it out away. So that's that first ray. The second ray is the one that goes through the vertex in this case. Okay, like I said, this is different order for different rays. So that's the one that comes parallel on either side. I don't tend to do that one. That one for me is sometimes a little bit harder. So that's not my favorite. Ray 3 is the one that I tend to do because it goes straight through. Once again, you're using dashed lines on the far side of the mirror because the light doesn't actually pass there. And so we can see right here is where all those intersect. Ray 4 is the one that would go parallel. So it comes in and then goes parallel. And then if you trace that parallel backwards, it's going to meet there. So I don't tend to use what they're calling Ray 2. I tend to use Ray 1, 3, and 4 if I'm trying to use 3 rays for more accuracy. Because you have to be careful. If you only do a couple, like 2 of the rays intersect here, or here, and those would not be good points of intersection. And we can see here that our image is virtual because our rays are not on the side of outgoing light. So our S prime would be here, and that would be a now negative value for our S prime. because that is giving us a virtual image. So we get that virtual image. It is upright and it is smaller. So if we were to like look at our magnification equation, that would be y prime over y. So we can see that our y prime is now smaller than y. So we're going to get a magnification that is less than 1. Our s prime is negative. So when you do a negative of a negative value on top for s prime and your positive for s on the bottom, the negative and negative cancel out to a positive, which is why we know that this is upright. Okay, so when we have that negative for that s prime, we're getting that upright image for that because of the getting canceled out with the negative that is written in the s prime equation. We don't need that negative here for the y's because both of our y's are positive. So that's also why we know that it's upright. It's virtual because it's on the far side. We can see that. We would be able to see that image with our eyes. We see the virtual images. So there's only one way to do this, so it doesn't matter where the object is, and this is always true, so it's a lot easier to just memorize kind of convex mirror behaviors or draw it once. But what's going to end up happening is if you move this object further away, that size, the magnification factor is going to change. So convex mirrors are used in the side rear view mirrors. Okay, objects may appear closer than they appear. They use these in grocery store aisle mirrors so that they can see what's going on in different locations. And there are many other applications of mirrors. So now what we're going to do is we're going to transition to lenses. So these are thin lenses. So we're not talking about some thick ball of glass. We're talking about something that we can consider mathematically thin. We don't have to worry about defining, in our case, what is thin or what is thick. There are different equations that apply for thicker materials, but we're going to focus on thin lenses. Now, you could have a simple lens, which is made from a single material. Our lenses are all going to have refractive indexes that are bigger than 1, so our n value is larger than 1. We could also have compound lenses. Compound lenses are going to be when you have several different lenses in a row. So there's a lot of camera lenses that do this, microscope lenses, telescope lenses. You'll have a whole bunch of them. And the reason you would have different ones is each lens is going to have its own properties. You might have a lens that creates a real image. Well, we can't see a real image, so then they'll pass that real image through a second lens that then converts it into a virtual image, which we can then see with our eyes. Or it may have, you may need a lens to flip an image upside down so it makes more sense in our head. So if the original lens inverts it, we need something to uninvert it. So lots of different applications of compound lenses. So our simple lens is going to have two surfaces. We're going to focus on spherical lenses for our purposes. And what happens is the light passes into the first surface and then is going to refract, so bend, and then the image forms on the inside of the lens, and then that light then passes through the other surface and is going to bend a second time. Now, that would be very difficult for us to track. So that's what a regular lens does, not necessarily a thin lens. So if we have a lens that's not thin, like this one here that's shown, then you would actually get this image here that's inverted, and then you would get that image would then have to pass through again, and it would have to bend back away, and so those light rays would pass through and then bend back away, and then we'd get another image. We'd have to deal with some virtually type stuff going through, but you would get another image out. That would be complicated. So the reason we use thin lenses is so that we can ignore that thickness. And we can assume that our lens is so small that no images form on the inside. So we need the thickness to be small compared to the radius of curvature. So we have converging and diverging lenses. So these are going to be our convex lenses, and these are going to be our concave lenses. Because once again, if you put your eye here, it bends out towards you. If you put your eye here, this bends in away from you. So when we look at the converging lenses, they're called converging lenses is because the rays will tend to bend towards and meet at the focal point. So with our converging lenses, our diverging lenses are going to do the opposite. They're going to refract away and bend away. So then our images are going to be formed by those virtual rays that pass back through in the opposite direction. So they meet on the opposite side than what happens if they were to converge. So these are going to behave differently. So converging lenses are always going to be thicker in the center. And our diverging lenses are going to be thicker at the edges. We're going to focus on these nice uniform shaped ones, but technically you could have flat sides, and this is still going to be a converging lens. This is still going to be a diverging lens. They don't have to be all nice and perfect. Now, one thing that is different is there are focal points on both sides of each lens. So if you picture here with our lens up top, this lens here, if you were to kind of continue through, is going to have a center of curvature that is over there on this side. This lens here, this side of the lens, is going to have a center of curvature that is actually over here on the opposite side. So, but remember, we are talking about where does the light rays go. So we look at the outgoing side. So we can see that our F and our C over here are on the outgoing side of the light. And when we looked at our sign conventions for those, that was what was really important, was the outgoing side of the light. Like I said, and our equations will take care of this. So technically there are two bends. The light rays are going to bend twice through the surfaces, but we do not need to worry about that. We can pretend that our lenses are thin so that if we draw the a line straight through the center, we can assume that our rays pass directly in towards the center and then straight through. So if we're going to bend, we're going to bend, but we're going to meet here. So we're going to assume there aren't two refractions, just one. Oh, and there it does it for me. Look at that. So we're going to assume that it meets here at that central axis and then bends only once. So when we draw our ray diagrams, we're going to do similar rays than what we had before. So ray 1 is the one that comes parallel and it goes through the focal point. Now it's going through our focal point that is on the far side, the outgoing side of the light. We don't worry about that on the opposite side. So we're looking at what's happening based on kind of that first side right there. So ray 2 passes through the F prime over here first and then goes parallel. So ray 1 goes through the lens and then goes through the regular F on the opposite side. Ray 2 passes through our F prime on the near side and then goes parallel. Those are the only two that I usually draw, but I like the parallel. For me, that makes me happy. But ray 3 goes straight through the center. So if you were to draw that vertical line here, it's going straight through the center. So that's also an easy one to draw. So I will sometimes use that just to double check and make sure that it's good. So if I was to have that image here would be upside down. So if our object is located between F and 2F, the image is real, inverted, and enlarged. Okay, and so that's what we have here. This is our center of curvature right here. Actually, that's technically C prime on that side and C over here. So if we're between F and 2F, the image is real, inverted, and enlarged. It's really hard at this location to see that this is actually bigger, but that image is actually larger. It's inverted and real. So once again, real images, we would not be able to see that image with our eyes if I was to put my eye right here. But if I was to put a screen, that image would be projected on the screen and I would be able to see that. If we are outside of 2F, so outside our center of curvature, then the image is going to be real, inverted, and reduced. So it's going to be smaller the further and further away we go. And it's still going to be real and inverted. So as long as we are outside of the focal point, we get a real image. It's inverted. When we're in here between C and F, then we get an enlarged image. If it was actually at the center of curvature, the image would be exactly the same size. So if you picture it, my image is going to be bigger the closer I am to F prime. And then if I pull it back, it's going to get smaller and smaller and smaller and smaller until it's the exact same size as the original image if I put my object on the center of curvature. And then beyond that, if I move the object back further, it's going to get smaller and smaller and smaller and smaller the further away that we go. Now, of course, interesting things happen when you go inside the focal point. So if you go inside the focal point, we are going to get that virtual image. It's always going to be upright and enlarged. So for example, if I was to put my object here inside the focal point, what would happen is that I would take this first ray, I'd come here, and I would go through my focal point. So that one would be the same. If I look at this green one, ray 3, that one's really easy to draw for this example, is I would come here through the center of curvature, or sorry, the central axis of that lens. And then it would keep on going. But as you can see, these two blue lines don't intersect. They're diverging. So what ends up happening is if I was to extend these rays backwards, and I was to look what happens, is eventually, sorry, I don't have a ruler, they are going to end up meeting. And I can see that what ends up happening is my image is now going to be virtual, because it is not on the side of outgoing. My outgoing side is over here. So this is a virtual image because it's not on the outgoing side. And I can see virtual images. So if I was to put my eye at this location, I would be able to see that arrow. And so you can see kind of how that would play out, how that one's a little bit different. Now, for our diverging lenses are always going to diverge. So once again, you're going to get the same behavior every time. So we come across, okay, our central axis here in the dead center is right here. So you have to bend away with a diverging lens. I don't know exactly where to bend away. So instead what I do is I go from that point of intersection and I go back and I trace back to the center F, and I put my ruler there. And then if I put my ruler there along that line, I can see that my ray has to diverge away and continue that same parallel path. So that's my first ray. Ray 2 has to go through the other F. And once again, this one's kind of weird. So you hit here at the center. That one's easier though, because it's going to come parallel off of that. So you just have to trace, if it were to go, picture that it could go all the way through F. It doesn't actually do that. It's going to bend. It's going to bend away from that path, but put your ruler directly from O to F prime and find where does it intersect there, and then you come parallel and you trace that refracted ray back over in this direction. So you can see we're starting to get a couple of different points of intersection. So there's a point of intersection here and a point of intersection there. Which one is it? Well, I'm not sure, so let's try another ray. So ray 3 passes directly through the center. So when I have that ray 3 passing through the center, then I can see that this location over here was the one that my image formed. So that's why you can do this with 2 rays, but it is much better to use 3. So this image is always virtual, upright, and reduced. So no matter where I was to move that, you're going to get that same behavior. Just the actual reduction in size is going to be different. So you could see this if I was to put my eye right here, I would be able to see that image. So with our values, we can see that our outgoing side is over here. And that affects our sign conventions. So you're going to get your virtual rays when we are not on the outcoming side. So whenever your image is not on the outgoing side, that's when you're going to get that virtual image. Our S prime is positive when we are on the outgoing side. So here, when we're back behind this lens, that's actually positive. This one here is a negative because we are not on the outgoing side. That's different than when you're dealing with mirrors, because on mirrors, the incoming and the outgoing are on the same side. With lenses, incoming and outgoing are on opposite sides. So you have to be really careful with those sign conventions. But what's nice is the equations are the exact same. So you only have to learn one set of equations, and you just want to make sure you're really careful with those sign conventions. So once you learn your sign conventions for mirrors, they're the same for lenses. You just have to be really careful because our definition of outgoing and incoming are in different locations. So as a summary of those sign conventions, just as a reminder, our object distance, this is for our object, so that would be S, is when the object is on the same side as the incoming light, our object distance is positive. And that's going to happen for us most of the time. The reason it wouldn't be is if you were dealing with compound lenses or mirrors and there were several different components, then that might be different. If our image distance, so that is our S prime, when the image is on the same side as the outgoing light, the image distance is positive. A positive image distance is real, negative image distance is virtual. The radius of curvature, and then therefore your focal point. When the center of curvature is on the same side as the outgoing light, R is positive, otherwise it's negative. And then our image height Y prime is positive if the image is upright, and it would be negative if the image is inverted. So we're going to work a problem. So once again, this is going to be for a lens, but the process is very similar for a mirror. The lenses I just find are a little trickier, so I really wanted to work a problem for the lens, but I linked a whole bunch of other videos in your lesson. All right, so we're going to work this example. We have an object located 5 centimeters in front of a converging lens of 10 centimeter focal length. We want to find the image distance and magnification and determine if the image is real or virtual. So they're not giving us the actual height of the object, although we can see that if we did know the height, we'd be able to find the height of the image. I'll show you how that works. And first thing I want to do is just go through and practice drawing this ray diagram. So we are inside the focal length. So even though this is a converging lens, when we're inside the focal length, our rays are actually going to diverge. So this is the exception to the rule, which is why I wanted to do one of these, because these are usually a little bit trickier. You'll get more practice with the others in the lab. So my first ray needs to pass through the focal points. We've got one and then the other, one that goes through each. So I can have the one that would pass through this focal point here. So what happens is this ray of light is going to come off, and it needs to hit the lens along the central axis. Our central axis is right here. So what ends up happening is that all of these rays are going to have to diverge. So when I draw this first one, it actually goes from the top up here to the central axis, but I wouldn't know exactly where that hits. So instead what I do is I put my ruler down, and when I put my ruler down, I'm going to trace that line backwards. It's dotted here because it doesn't actually go that way. The light doesn't travel that way. But I figure out what's parallel, and that allows me to draw this part here. And then once it hits, it goes parallel to my principal axis. And then I can trace those dotted lines backwards because I know that this is going to diverge. So my second one goes to the other focal point. So once again, I'm going to come parallel across. This one does actually pass through, but I can see that these two arrows are diverging, which is why I need to trace those rays backwards. And you always trace the refracted ray back. So this is my refracted ray here. So if I trace that backwards here, I can see that we're meeting up right back here. I could draw the one through the central axis, and I can see that, yes, all three of those rays are going to meet up. So if I was to draw my image, I can see that those are going to converge kind of close. I didn't quite get that arrow. I think it got shifted. And also just hand drawing everything and not having everything like exactly kind of symmetrical. So in this case, my image should be approximately right there near that focal length. So how could I actually prove that that's kind of where my image should be? We can use our mirror and lens equations. So as this was formed by the virtual rays, this is a virtual image. Okay, so we figure out that this is actually a virtual image. It would be real if it converged on the side of the outgoing light. Our outgoing light is over here. And so what ends up happening is we can use our equations. I have 1 over s plus 1 over s prime is equal to 1 over f. So s is going to be my distance between the object and the center of that lens, which is going to be my 5 centimeters. And then my f is the focal length, which is that distance here, which is 10 centimeters. So if I wanted to find s prime, first I'm going to subtract the 1 over s to the other side. So I get 1 over s prime is equal to 1 over f minus 1 over s. And then to actually find s prime, I'm going to have to undo that inverted. So I'm going to have to raise the power of -1 on both sides. You could go to the effort of getting a common denominator, but I usually just plug in. So my s prime is going to be 1 over f minus 1 over s to the -1. So that's going to be, my focal length is 1 over 10 minus 1 over my object distance, which is 1 over 5 to the -1. If I was doing this without a calculator, I could actually get a common denominator. I could get a common denominator. I could do 2 over 10. So I get 1 minus 2 is a -1 over 10. And then I can flip that up, invert that. And so I get -10 centimeters for my s prime. And so that's how I know that my s prime is going to be in the same location as my focal point over here, because my focal point's at 10 centimeters. And it's negative because we have that virtual image, because we are not on the side of the outgoing light. So if I wanted to find my magnification is equal to y prime over y, or negative s prime over s. So we don't know any information about height, so I can use just the right, m is equal to negative s prime over s. Well, my s prime is the -10 centimeters divided by my s, which is 5 centimeters. The negatives cancel, so I get that my magnification is equal to a +2. The positive tells me that I am upright. 2 tells me that my image should be twice the height as the original object. So I might not get that exactly perfect with my ray diagrams, but you can see that that was close. Now, if I had my value for y, my original height, then what I could do is, once I have my magnification, I could use this side right here and I could find y prime. So I could use that there. And so this process is going to be similar whether you're using lenses or mirrors. We just have to be careful with our sign conventions and understanding those sign conventions. All right, thank you. Have a good day.